Say thank you all for coming. I know some of you have come from quite far away to be here. We came from London ourselves yesterday, so it's a bit of a trek to come all the way to Dundee, but it's always great to be back for Securi-Tay. Second thing was that actually Graham is speaking next door, and he's a great presenter, who, thank you for picking us. And his talk is recorded as well, so I'd catch that after the presentation. But our presentation is Mobile Application Hardening, Protecting Business Critical Apps. And for the benefit of those in the room that don't know what app hardening is, it's essentially just making an application harder to attack. So first of all, who are we? I'm Cucakovic, and this is Grant Douglas. We're security consultants at Synopsys working with SIG, which is the software integrity group. Between us, we have a number of years' experience working with Android applications, iOS applications, and we've tested a whole load of different apps, from financial apps, games apps, medical apps, you name it, we've probably tested it. And both of us as well are actually Aberdeen alumni. Grant graduated in ethical hacking, and I graduated in digital forensics. So, mandatory Synopsys slide. I'm sure Nick covered this already this morning during his keynote. But historically, Synopsys is a hardware company that moved into the EDA space, a hardware company that worked in the EDA space to automate chip design, and they moved into software integrity a few years back. And they achieved this by acquiring a number of popular security companies, so Coverity, Canonical, and Digital, which is the company that we used to work for. Thank you, Nick. And Black Duck most recently. So we do a lot of security activities, not just pen testing. We do threat modeling, architecture analysis, code review, training, a whole load of other things. If you're interested, feel free to stop by the stand afterwards. But with that, let's get into the meat of the presentation. So first of all, I'll be introducing you to what is a business critical application and what kinds of apps we see go the extra mile to harden themselves. We'll then be talking about some of the common hardening techniques. So it was kind of difficult for this presentation to choose what we should focus in on, because there's obviously so many different areas of app hardening, so we've chosen on a few key ones, and we're going to give you a top-down approach, looking at some basic checks, some intermediary checks, and looking at some very advanced checks. We're then going to be moving on to actually talking about how you can break these controls and sidestep these controls at each level, and we'll illustrate to you the kinds of level of skill you would need for each of them. And then finally, we'll be giving you an overview of some best practices we've seen and just generally some tips and tricks that we found from testing these kinds of applications. So what kind of applications have we seen go that extra mile? Well, it all depends really on the application's threat model is the short answer, but conventionally it's things that have access to documents that are sensitive to the company, for example, something that's handling sensitive or private identifying information, like a medical application, or even something that has very sensitive IP. For example, if you had a games application that had a very effective algorithm for parsing something, you probably want to make it harder for a third party to understand what you're doing there and hide from competitors. Another thing might be if the actual application account itself has worth. So the best way to kind of articulate this is, for example, Snapchat. Your actual Snapchat handle has value, right? And if you have an especially short handle, someone else having access to that probably isn't a good thing. And financial companies as well. So to limit fraud and that kind of stuff, they'll usually go above and beyond. But this isn't necessarily to say that just because you're one of these kinds of applications, you need to do app hardening. Again, it all depends on your appetite to risk and threat model of the company. So, what will a threat actor or an attacker actually do to attack an application? What's their kind of methodology or step-by-step process? Well, the first thing you'd probably do is find an application to attack, right? You'd go in the Google Play Store or App Store, find something you want to hit. And the first point of call in that process is to do static analysis. For most of you in the room, I'm sure you're aware what static analysis is. But for those of you who aren't, it's essentially the technique of analyzing an application when it's completely at rest. So when it's not running. And you'd be looking to identify data value, code value, and identify controls of interest. And you'll probably do this by, for example, unzipping the binary, seeing what assets there are, or even using a decompiler. For those of you that aren't familiar with a decompiler, it's essentially just a tool you can use to give you a source code representation of a compiled library. So it kind of gives you an understanding of what the original source code did. So, for example, if you're looking for data value, you might look for configuration files to see how the app's put together. Code value, if they had, for example, some crypto functions, you might look to see what kinds of crypto it's implementing. And you might look to identify controls of interest. Let's say you found, an admin function, right? You go to see where that's using the application, see what kinds of values it's returning, where it's run, that kind of stuff. The next step would probably be to move into dynamic analysis. And this is, again, just where you're analyzing an application where it's running. So you'd feed on from your static analysis portion, again, looking for data value, code value, and controls of interest to see how it's used in the application when it's running. So once you identify something that you want to attack, you'd probably then try to develop a bypass. So just using the previous example, the isAdmin function, you'll try to manipulate that in some way, shape, or form to always make you an admin, that kind of stuff. And if they have lots of these controls in place, you might automate the process of finding these controls and script it so you don't have to feed them all individually. And if you're a malicious attacker, you might actually try to build payloads as part of this. So you might take that admin bypass, build it into some malware, and use that to siphon off data, for example. And you might try to distribute these payloads as well on forums, third-party app stores, that kind of stuff. So I'll start off with the initial analysis portion, so looking at static analysis, and I'll hand over to Grant to talk about the dynamic analysis portion later on. So some of the tools that somebody would use to statically analyze your application are Radare, for example, which is a reverse engineering framework. We'll go over it today. And historically it was used for malware reverse engineering, but it's very versatile and can be used in a number of different ways. Jeb, which is a decompiler for the Java space and Kotlin space mainly. IDA Pro, which has some decompiling capabilities. It does a lot more than that, but that's what we'll be looking at today. And Hopper Disassembler, which is essentially just a budget version of IDA Pro. And they'll be using these tools to look for interesting signatures. So like I said before, code value, data value, controls value, you'll be looking for strings, class names, method names. So going back to the isAdmin function, you look to see where, if they had a string that said, you're not an admin, you'd go to see where that string is referenced in the code base to see where the admin function is to further understand how it works. Class names, as an example, if you had a class in a games application called microtransaction, you go to see where that's leveraged, understand how that code looks like, and then look for method names. For example, if they had a payment function within that, you try to understand how that works underneath the hood. And you might even look for interesting APIs, for example, networking APIs to see how it's sending traffic, again, crypto APIs to see what kind of crypto it's using, if any, and looking for file I/O operations to see what files it's opening on disk. And you might look for known vulnerable components or dependencies. So instead of attacking the application directly, you might attack a component which it leverages. Additionally, something to point out is that an attacker might actually patch the application statically. So from that decompiled code, they might patch an instruction out and put it back together. So for example, that isAdmin function, instead of if equals, if not equals, so it always returns you're an admin. Or modify the execution flow in general to make it in your favor to change the original functionality. So what does this actually look like in practice? So as you can see here, there's just some source code that we put together in Objective-C, a very simple function that is a view to onload. So whenever the view loads, this function is invoked. And as you can see there, we've got a label saying, please log in. We have a path calling out to Cydia, and we're using the access API to see if that path exists, and we're printing the result of that operation. When we compile the application and then decompile it using IDA, you can see that there's a number of similarities, right? You can see that view did onload function, you can see that please log in string, you can see the same path calling out to Cydia, and you can see us calling out to the access API, and again printing the result of that operation. And this isn't just for Objective-C, this also works in the Kotlin space and the Java space as well, so it works in a number of languages. So as you can see here in this Kotlin application, we've got a function called rootcheck, looking to see if the xbin/su path exists. Depending on if it exists or not, we're returning true, and if not, we're returning false. When we compile this and then decompile it, in this example I've used Jeb, you can see a number of similarities there, right? You can see the rootcheck function, you can see again the xbin/su path, and you can see that we're calling out to the exists API to see if that file exists or that path exists, and returning true or false, depending on the outcome. Right, so obviously if somebody's just compiling the code and decompiling it, you can get a pretty reasonable estimation of what that code's doing. How can we make it harder for an attacker to actually look at that code and make their life much more difficult to reverse engineer the application? Well, the short answer is to use obfuscation. So obfuscation is probably best illustrated here through renaming. So I'll go over renaming first, but there's essentially tools you can build into a pipeline that will do this as an extra operation as part of your compilation. So in this class here, you can see there's a class called sample with a variable called 42. And when the view loads, we're calling out to foo, which increments the value 42 by 1. So each time the view loads, it'll be 42, 43, 44, and so on and so forth. When we compile this using an obfuscator, in this example I've used, I think it's the Cyrus or Sirius obfuscator. I'm not sure if they're trying to go for a pun, but it's an open source obfuscator. You can find it online. You can see when we're renaming, when we use rename obfuscation, you can see the class that was previously sample is now being renamed to some random strings. The variable that was previously value is now changed as well. And the function that was previously foo is now renamed. So what to take away from this is that it just makes the code a little bit harder to read, right? And this is just one of the many ways you can make it harder to understand what the source code is doing from a reverse engineering perspective. Another technique you can use in regards to obfuscation is control flow obfuscation. And this one's a little bit more interesting because the premise behind it is making an application's logic difficult to follow and understand without actually modifying the underlying functionality. So previously with the renaming obfuscation, that was just renaming the variables and keeping the underlying functionality. This is doing much of the same, but making the actual flow of the application harder to follow. And the best way to kind of represent this is, it's a bit like giving bad directions. So instead of going from point A to B, you go from point A to B to C to D and then finally to E. So you're just adding some steps in between. Some example variants of control flow obfuscation, function splicing. So if you take one function, you can splice that into a series of smaller functions. Or you could do method merging, where you take a bunch of smaller functions and merge it into one big function. And that again makes it harder to understand, what each individual function is doing. Or in particular, you could do method inlining. And method inlining is particularly important because you'll see later on in the presentation that this can have benefits as well, but we'll cover that a bit later on. So method inlining is where you essentially cut out the invocation of a function and take the body of that function in the place you're calling it. So as you can see here, we've got an app on the left that's calling out to the security check function. If we were to inline this function, we would simply take the body of it and put it in place of where we're calling to the function. So we're just cutting out the function entirely. And the advantage of doing this means that instead of having a single point that you can attack as an attacker, you then have multiple instances of this in memory. And this also makes it difficult for somebody to see where that function is used within the rest of the code base, because you won't be able to easily cross-reference where it's used. And you can do other cool things like junk insertion, where you just add random junk arbitrary operations to make it harder to understand what's, core to the application and what isn't. And there's a whole load of different other control flow obfuscation techniques. But what this actually looks like graphically is, on the left-hand side, you can see the original control flow graph for application. You can see it's pretty simple, pretty straightforward. As you apply more control flow obfuscation, you can see that it becomes harder and harder to understand what the application is doing, and it becomes more and more convoluted. And something important to note here as well is that you're constantly in a battle with the actual compiler. So by inserting junk code, obviously one of the compiler's jobs is to remove junk code, right? To make it as efficient as possible. So you're constantly at a fight of, adding obfuscation while fighting with performance, because obviously if you're adding junk code, it's doing more processing. So there's definitely a balance to be struck there. And even with just these two techniques, I just put a dummy application together here. You can see that it becomes very difficult to actually read what the code is doing. There's actual legitimate code hidden within this, and it just becomes a nightmare to actually read what's going on. And if you start to apply more advanced obfuscation techniques that we won't be covering today, you can end up with code like this. This was just a sample app that I found off the Google Play Store. And this is doing a bunch of really interesting things. It's doing renaming obfuscation, control flow obfuscation, and it's even doing illegal characters. So the code here actually breaks decompilers. So I was using a cheap decompiler called JDGUI, and I wasn't able to even decompile the application. So you can do some advanced things to make it even harder for an attacker to analyze the source code statically, and overall make it harder for them to move into the dynamic analysis portion. And with that, I'll hand over to Grant to talk about dynamic analysis.
Cool. So, yeah, basically, as Nick's shown you, there's like a bunch of stuff that an attacker's going to do before they even run the app, right? They're going to look at all the classes, the methods, find out the stuff that they want to attack, whether that's transaction APIs, or whether that's, the access rights you have within the application, or many other things. So as applications start to put in obfuscation and renaming and anti-disassembly and anti-decompilation, we tend to move towards dynamic analysis, so that we can actually run the app and see how things work, and in many ways we can even emulate over some of the obfuscation to just get rid of the junk code, to make it easier to understand. So one of the tools that we want to talk about today is called Frida. And Frida, hands up if you've heard of Frida. Keep your hands up if you've used Frida. Keep your hands up if you wrote Frida. Awesome. So yeah, for those of you that are not familiar with it, it's what's called a dynamic binary instrumentation framework. So what that means is it allows you to, at runtime, connect to a process, and you can invoke code in the process, you can change code in the process, you can inspect memory and do various things. It's not necessarily a hacking tool per se, but it's good for us as security researchers. Frida is open source, it's in GitHub. The folks behind Frida are very welcoming. So if you have issues and stuff, you can just reach out on GitHub and get some help. And for us as security researchers, it's really nice because Frida actually has a bunch of different language bindings. Just a couple of examples that might be more familiar, C and C++ bindings, so you can instrument Frida from native code. If you want to, you can write Python tools that will run your Frida modules as well. But they have other language bindings in Swift, Ruby, you name it. They've pretty much got most of the modern languages. But for the most part, Frida is a JavaScript bridge. So you have to, no matter if you're using Python or C or anything like that, you still have to work with the JavaScript side of things. The entire Frida SDK is JavaScript. So even in your Python code, you'll still have to put JavaScript payloads that you'll insert into the apps. One thing I didn't mention is that Frida is supported on multiple platforms, and I don't just mean like you can run Frida from a Mac or Windows or Linux, but you can actually use Frida against apps on all of those platforms as well. So it's not just Android, it's not just iPhone like we're showing today, but you can use it against Windows apps, you can use it against Linux apps, and back in the day that's what Frida was used for more often. So the kind of, the typical use cases, I guess, with Frida would be to inspect the memory of a process, maybe modify the memory of a process. So again, this could be looking for cryptographic keys or secrets or passwords. But it also allows you to do this thing called hooking, which basically is a way where you can target a specific function and you want to change its behavior. So again, in Nick's example, when he was talking about having an isAdmin function that returns true or false, then I think it would be really nice if we could just make it return true so that we get admin privileges, right? If the app's good, then, that's not going to work because they do stuff on the web server side, but we can at least try it and see what happens. So the typical use case that we'll be covering today is to replace code inside a target process. So it's not that important, but Frida has two main modes of operation. One is called Frida Server, which is what we're going to be using today. So this requires you to use a rooted device or a jailbroken iPhone. But the other mode is called Frida Gadget, which allows you to do this without a rooted device. So you can basically force Frida into an app and then reinstall it onto a phone. So the only reason I bring this up is because if you're inspired by any of this and you want to have a play with it later on, then you can go ahead and you can use this afterwards even if you don't have a jailbroken device. So yeah, that's just the reason I brought it up. But for today, we're using Frida Server. So one of the most interesting components for us as security researchers of Frida is this component called Interceptor. And as the name would suggest, it's for intercepting functionality inside the app. So you can use it to change things, right? So this allows us to specify a function and analyze things like its inputs. So if you think of like a login function, typically would receive a username and a password, right? So when that function's called, we can actually take the username and password and we can log it, or we can send it off to a malicious server if we're writing some malware or something like that. But it also allows us to see the return values as well. So let's say they have a random number generator or they have a function to generate an encryption key, then we can use Interceptor to target that function, and when it generates the key, we can steal a copy of it so that we can see everything else the app does. So it's very, very powerful, very easy to use, and thankfully nowadays pretty well documented. Wasn't always well documented, but those guys are doing a much better job now. So one thing to note is on the Java side, on Android, you're not going to be using Interceptor so much. Interceptor is used on Objective-C for iOS and also for native code, like pure native code written in C. But on the Java side of things, it works slightly different, but I'm not going to go into it because, as I say, it's pretty well documented now. So check out the website. It's got documentation and examples and all that kind of stuff. Loads of blog posts. If you want to know more, come and ask us afterwards. Not, well, kind of. Not really. There's a few tricks. We could chat afterwards about it, but there's a conference. So these guys wrote Radare and Frida. So one of their static analysis tools was written by the same guys. They have a conference in Barcelona every September, and this last year someone presented like Frida with Swift, and they're trying to put together some implementation that allows you to do some things. But you can target Swift functionality. It's when you want to start doing stuff with the objects themselves. But yeah, as I say, we can pick it up afterwards. So the final thing to note is we don't just get to see usernames and passwords or any of the inputs and return values, but we can change them. So again, in the isAdmin function, we can make it return true. If they're generating a random number, we can make it return 1337 every time. Like, we can do literally anything we want with the app, right? We're in full control of it. So to give you a quick example, as not really too visible, but the things to note here is at the top, we have a way in the JavaScript to access classes. So through Frida, it exposes a list of all the classes that are inside the app. You don't need to tell it about them, it'll tell you them. So in this case, we have a class called the payment controller, and in the right-hand arrow in the green text, we have a function called send money to an account. So this function takes an account number and a sort code and an amount. So this might be like a financial app or a crypto app or something like that. And once you have a reference to it, all you do is you pass it into Interceptor. And Interceptor is really nice. It gives you two optional code blocks. So you get an on-enter, which is like just prior to the function running, you want to do something. So again, in the username and password example, that would be what we would want to do. We'd want to steal things as the function is about to run. But if we want to change things after it's run, like the return value, then we would use the onLeave. So in this case, we simply parse the account number, sort code, and amount, and we get them in JavaScript objects that we can interact with. We just write them out to the console. So in Frida, you have a terminal. You can just see the values written there. But if we were maybe more malicious, we would be sending them to an external server or something like that. And then finally, just to give you an example of what it looks like at the bottom, we're actually replacing the account number with 010101 and, changing the amount, let's say from £50 to 500. So this would be an example of how we could hijack a transaction. If Alice is sending Bob £50, then she's now going to send us £500 instead. And you could get particularly nasty with the malware because even on the next screen, when your banking app says, hey, do you want to send Grant 500? We could just change the whole view. So it says, do you really want to send Bob 50? And of course they say, yeah. And even when they look at the bank statement, we can make it so it says 50 and it went to Bob, because we control everything, right? So, if Frida is in the app, then you can do some pretty nasty stuff. And it's not just at the Objective-C layer or the Java layer, as I was saying. You can also do things like this. So we have an API called Access. Not too important, but Access allows you to interact with the file system and check if, for example, if files exist. So all we're doing here is we're printing out the path, and the path would be in register x0, which is ARM64. So basically, whenever the app calls Access, we're just logging the file paths that are being searched for. And it'll become clear in a few slides why we would want to look at things like file paths. So this all kind of sounds a little bit like sorcery, and some of you in the room probably have used Frida before, so you're familiar with this, but other people who are hearing this for the first time probably sounds a bit like witchcraft. So how does hooking work? Well, it uses a really long-standing technique called code trampolines, and code trampolines have been around for way longer than Frida. And basically it's a way to literally bounce, hence the name trampoline. It's a way to bounce execution from a target function to us instead. So how does that look? Well, in this case, we have an app and we have the standard library. So we might be calling the access function that we just mentioned to check for a file path. So what typically happens is the app calls access. This is without Frida and without any hooking. And the access function runs with a little wiggle. And when it's done, it passes execution back to the app. Simple, right? It's how applications call out to standard library code. Now, if we hook it with Frida, what happens is Frida inserts one of these trampolines into the target function, and it also puts our replacement code in memory somewhere. So if we're doing something like logging the file path or changing the file path, then obviously that code needs to be in memory. So now what happens is the app calls access, and the very first thing that happens instantly is the trampoline code runs. And it's a really small set of instructions. Its sole responsibility is just to hijack execution. So what it does, it just passes us over to the replacement function, and now we run instead. And when we're done, optionally, we can pass back execution to the original function. We don't have to, but let's in this case say that we do, and then finally execution goes back to the app. Now the reason that part is optional, and in most cases you probably want to do it, so if I go back to the example of stealing a username and password, you can imagine if all of us in the room tomorrow went into our banking app, typed in our username and our password and hit login and nothing happens, probably a good number of us will report it to the bank or to the games company that we're working for, right? And after a number of these reports, they'll start looking into it and they'll find out something weird is going on, and probably at some point they'll figure it out. But if you type in your username and password and hit login and you get logged in, then you don't notice anything. So in a lot of cases, depending on your goal, then you're usually going to pass execution back to the main function. Another reason would be if that function is really complex, then you don't want to have to re-implement everything it does. You might just want to change its inputs or outputs and then just let it do its thing, right? So just let it do whatever it was meant to do naturally. So again, kind of sounds a little bit like witchcraft. It might make sense, it might not. So we put together a little demo. Again, this might not be super visible, but on the right-hand side we have an iPad with Twitter, and we're not doing anything with Frida. We just open up my boring profile. And you'll notice my name's Grant Douglas. I have a really uninteresting bio, just says where I work and I like mobile stuff. But if we go ahead and kill the app, and then this time we're going to run it with a Frida script that we've written just to give you a quick demo of what you could do. So this is what the Frida console looks like on the left. So you can see our logs in the bottom left says placing bio and placing name. So now when we revisit the profile, we'll notice things look a little bit different. So in this case, I should point out this is not happening on Twitter side. This is only in the app, so I'm not actually hacking Twitter in any way. But now you can see it says Average Hackers Rule and greets from Securi-Tay 2019. So just a quick visual demo of like how this stuff looks. So a couple of slides ago we mentioned that to use Frida Server, in this case you require a rooted device or a jailbroken iPhone. Hands up how many people would be comfortable explaining what a rooted device is or a jailbroken iPhone is? A few. How many people have a rooted Android phone or a jailbroken iPhone? Okay. This is not a criticism in the next few bullets, by the way. So basically, jailbreaking is the process to gain more control over your device. And right, for the most part, if you're like super tech savvy, then maybe there's an argument to say that you're probably comfortable working with it. In the industry, we have lots of jailbroken and rooted devices to do our assessments. You have to just be very cautious about what you're doing. But for those of you that don't know what jailbroken devices or rooted devices are, it's basically a way of disabling all these controls to allow you to do more with your phone. And it typically comes packaged as some software that runs on either on your laptop or your computer, or sometimes it's an app that actually runs on the phone like this one, and it has a big button that says jailbreak or root. You click it, and then it does a bunch of magic, and the device becomes rooted. What's important to note is that this software is actually exploiting real vulnerabilities on the phone. So these researchers go out there and they find like vulnerabilities in the platform on Android and iPhone, and then they write some payloads that disable the controls. But in the real world, those payloads might be to exfiltrate data or to install a backdoor. So these payloads are less malicious, or at least we hope they are. We don't really know too much about what they're doing. But in this case, we're just disabling a bunch of the security controls on the device. Now, why would you want to do that? Well, it allows you to do a bunch of cool things. So you can run untrusted code, so things that aren't approved by Apple and Google, you can run them. And for example, not as exciting to Android users, but in the iPhone world, things like this are pretty cool. It looks a lot better than the stock iPhone. You can add themes. You can also make it so all your notifications are the same color as the originating app, which Apple should really make a feature because that's pretty cool. And then you can do things like this. So if you have a really annoying friend, you can delay the read receipt so you read the message and they don't find out for half an hour or an hour or even 6 hours later if you want to. So just small aesthetic changes and, performance enhancements and things like that. Nothing too serious, right? But despite that, there exists this thing called jailbreak detection. Or root detection in the Android scene. And for those of you that put your hand up and said you use a rooted device or a jailbroken iPhone, you've probably seen screens like this. This is, I think, Santander. It just says, yeah, your device has been jailbroken. We have Pokemon Go. It says, yeah, your device is not compatible. And then finally, we've got one that's from Skype that says you've got a modified operating system. So some of these apps will take it upon themselves to block you from using them if they detect the device is in that state. So if all we're doing is adding themes and delaying the messages to that annoying friend, then what's the big deal? Why is my bank or the game I want to play deciding to stop us from doing that? Why should they take the onus on them? Well, because as I mentioned a few slides ago, we're actually disabling a bunch of the security on the device, and for the most part, that is to protect us. Now, I'm not saying Apple and Google don't have a vested interest to stop these things because of things like app piracy and stuff, but in general, those controls are meant to protect us. Now, as security researchers, we have a good reason to want to root and jailbreak these devices. But for end consumers, it depends on who it is. If non-tech savvy family members, probably not sensible, but again, if you feel you're pretty tech proficient, then I guess it's up to you to take that decision. So how do these apps actually know though? Well, once you start disabling a bunch of controls on the device, or you run the jailbreak process, like a bunch of things change. So the file system changes, new directories are created, new files exist that didn't exist before. You might even have like behavioral differences, right? So if you call a function on a clean iPhone, which is not jailbroken, or a clean rooted Android phone, or non-rooted Android phone, then it might do one thing, but then if you do the same thing on a rooted device or a jailbroken device, then you notice a difference, right? And if there's a difference, then it means it's detectable. Again, the absence of controls. So for those of you that don't know, on iPhone and Android, apps can't interact with each other. So like Facebook can't go into Google Mail's app folder and take out the data. Like they're not allowed to do that, right? So in general, applications can't access the file system outside of their directory. Loosely, it's a generalization, but in most cases, they can't access the file system outside the directory. So if, for example, you were to try and create a new file out with the folder and it works, then again, like the controls have been disabled. So there's a bunch of easy ways that apps can do this. And finally, detecting installed packages. So typically, you have third-party app stores and that kind of stuff. You can just detect the presence of these as well. So we have like a really basic example of what jailbreak detection might look like. So this is, again, written in Objective-C, really horrible syntax for anyone who has never seen Objective-C before. But the important thing to realize is we have 3 checks. One looks for Cydia.app, which is the third-party app store. And the next 2 are looking for files related to APT, which is one of the common package managers for Linux-based systems and is the package manager that iPhone uses once it's jailbroken. So this is, again, really basic, but it's not actually out of line with what you would see in most apps. They do really basic stuff, and usually it's copy and pasted from Stack Overflow or GitHub or something like that, so it's not amazing. But we can target these checks in Frida really easily. So if we were to run this app, we might get a message that looks like this, saying, hey, the device is dirty, all right? So the app knows that the device isn't trusted. But if we want to, we can attach with Frida. And in this case, you'll notice that our Frida script, in our logs, we can see the files that they're searching for. We haven't told our Frida script what they're looking for. We just log everything they do check for. And in this case, we can say return false. And instead of looking for those 2 files, we can make them look for Apate hackers, which doesn't exist. And then the device comes back and looks like this, saying, hey, the device is clean. So just a really basic example of how you could bypass this stuff. So to recap on what we've covered so far, the first thing someone's going to do is they're going to go out in the App Store, they're going to grab your app or maybe even potentially multiple apps, and they're going to start to analyze the files, probably in some kind of automated fashion. They're going to decompile them, look at the libraries that are in them, identify any controls that they might need to bypass, any functionality they want to abuse, any vulnerabilities they can spot. And once they find that functionality, they're going to write some attack payloads. Support to note, Frida is not the only tool out there. There's many public tools that you can use, and probably, in the likes of the malware world, those guys are probably doing some of their own custom stuff as well. But Frida is kind of the de facto standard. So in this case, we'll say they'll write something in Frida. And again, if you have like copy and pasted controls from GitHub and Stack Overflow, and that kind of thing, then you can expect someone's going to bypass them super easy because they're documented online. So, with that, we're going to show, okay, so these are like some basic stuff, right? So we know that you can have some checks, you can look for files, you could even go from writing these things in Java to writing them in C. So can someone go any further, right? Is it game over for developers, or can they do something a little bit sneakier to try and hide what they're doing? Well, the answer is yes. So how many people are familiar with syscalls? Okay, more than I thought. Okay, cool. So for everyone in the room who's worked extensively with operating systems, you'll be obviously very familiar with this. If you're into mobile reverse engineering, then you probably come across this as well. A system call is basically used in most modern operating systems. In fact, probably all of at least the most used operating systems. And it's a way for applications to invoke code inside the kernel. So, things like file access, accessing the disk, networking, process management is all handled by the kernel. So we basically need a mechanism for applications to reach out and make use of that. And you typically don't ever interact with this stuff directly. So, as the example earlier, you call the access function if you want to access a file on disk. In this case, if we want to exit the app because we've detected something fishy, then we call the exit function. We don't really ever have visibility into what's happening at the syscall layer down beneath, right? So we don't really interact with these. And in general, there's a ballpark figure. There's at least on Android and iOS, there's several hundred of these. The numbers go beyond 500, but I think in total there's around 400 and something. And they're documented online, so the Android syscall table is inherited from Linux, so you can go check it out. The iOS one is also documented, so you can see what all the APIs map to. But again, that's I think it's documented as iOS 6. So there's a tool out there called Joker, which is really cool, and you can basically pass in like an iOS firmware. So in this case, we took iOS 12, which is the most up-to-date. And you just download it, unzip it, pass it into the tool, and with -s, you can tell it to print me all the syscalls. These don't really ever change, so even though the list online is iOS 6, doesn't really change all that often. But if you want to be sure you're working with the up-to-date list, then you can go ahead and do it. So we have 1 is exit, 4 is write, 5 is open. So these are all the different APIs we might call. These will be the mappings behind the scenes. One that's important to remember is exit is 1. So in the next example, we're going to be looking at exit. So just remember, exit is 1. And the actual instructions for this we'll show you in a slide or two. So if we know that someone's going to attack our application and hook our code and even the standard library functions that we're using and log what we're doing and control it and change how it behaves, then in theory, why don't we just skip the middleman? So instead of calling the standard library, we know that the standard library is just going to pass these messages on to the kernel to do those things. So why don't we just go ahead and do that ourselves? So this is what, people in the gaming world and financials and stuff, people who are going that extra mile, they started to look at these things and use them to try and better improve the confidence in their controls. So if we take a look at this as an example, again, apologies, the lighting's not great. But on the left, this is the traditional approach. So we're calling exit and we pass in a value of -1. So again, we might have detected something. We want to exit the app. You call exit, and what happens at the instruction level, you don't need to care too much, is we just branch into the standard library and it runs the exit function. It takes care of it for you. Right? So that's the traditional approach. So what we want to do instead is we can actually put some instructions in our app directly without actually writing code. We're putting instructions straight in. And what those instructions are doing, if you look at this line here, we have a value of 1, which we just said is the value for exit. And when these instructions are run, what happens is the kernel will say, okay, they're running the syscall for exit, it's time to kill that process. So if someone was hooking the exit function, then they wouldn't actually see us do this. So we would have slipped past them. So again, it's just a sneakier way of doing this. One thing to point out is the instruction svc OX80 is the interrupt for syscalls on iOS, and it's svc 0 on Android. So in the next example, we'll show you how we can actually find those things. So speaking of finding them, can we still do it? Is Frida still capable? The answer is yes, although it's not really well documented. So Frida doesn't just allow you to attack functions, but you can give it the addresses and offsets of specific instructions that you want to attack as well. And it will handle it just the same way. So it will insert a trampoline and you can hijack execution. So in this case, we have, again, some application we've written ourselves. We're using access this time to check for a file on disk. And on the left, we have IDA Pro, and we can see the svc OX80 instruction. You probably can't read the address, but it's 6544, nothing interesting. But because the app's not running, we need to calculate where that instruction would be when the app is running because of ASLR. So what you need to do is you need to add on the base address of the process to calculate the address at runtime. And then you just pass it to interceptor.attach like you would normally. And then we can print out the file path just like we did. So again, come and see us afterwards if you want to see these examples. The light's not great, but now when we run the application, we click the check tamper. You can see we have a file path, secret Securi-Tay file 2019. And you can also see in orange, if you squint, it says instruction at pointer svc OX80. So what we're doing is, in Frida, you can even give it an address and say, tell me the actual readable instruction that's there. So what we do is when we calculate where we think it is, we're just printing out as a sanity check to say, okay, if that said like move something, then we know we're in the wrong place. So we just print it for like debugging reasons. So that's like how we could actually go ahead and find these things. But if we're doing these kind of assessments, like you might only have a small window. So Nick's going to talk a little bit more about how we've tried to improve on that.
So as you can see from Grant's example there, actually going into the application, finding that offset, putting it into a Frida hook, calculating off the base address, and then writing a hook to then, hook the function, it's pretty time consuming. And if you're doing pen tests like we are for 5 or 10 day windows, there's no way you could, find all of these, if they're implementing tens, hundreds, or even thousands of these calls. So what we've done internally is actually start moving towards automating this, and what we've done is write a tool in Radare to essentially automate this process for us. So the way this works is that you simply pass in a iOS app. It looks at the file, tries to find all these SVC calls, look for what value is being passed into SVC80, and then prints the result of the address of, or offset that this is at. So as you can see there, we've got a call for access and a call for unknown. And something important to note here is that then, this kind of static analysis tooling could then feed into dynamic analysis tooling. So you could then generate Frida scripts that you can then use to bypass the stuff automatically to get past it very quickly, to help you in a 5 or 10 day assessment. But throughout this presentation, we've really just kind of talked to you about, syscalls in a very theoretical sense, like what kinds of applications are doing this? Are people actually, in the wild doing this? And just in this example here, we threw Fortnite into our tool. I'm sure many of you are familiar with it, but essentially you can see that it's calling out to a number of syscalls. You can see access, you can see unlink, symlink, stat64, and a whole load of different unknown syscalls which we can't verify statically because they're using some obfuscation to make it harder to see what's going on. So this is actually something that people are doing out in the wild. And something important to note is that this tooling that we've started to right now, it's very in early days. I think going forward, our objective is kind of share it as much as we can, but we'll see where that goes. So to give you some numbers how this looks outside of just Fortnite, we've got 10 applications here that we found from the App Store, from banking applications, gaming applications to medical applications. It's only 10 apps, but this is in line with what we've seen from the whole load of testing that we've done internally. So you can see that banking applications or financial applications are going quite close to using syscalls. They're implementing it quite frequently, followed by games applications, which are, moving up to the hundreds, and then followed by medical applications. And something important to note here is that this isn't a representation to say that, banking apps are better than medical apps or gaming apps. It's all dependent on the amount of syscalls. It doesn't really factor anything. It's just to show you that they're using them. So, taking a look back at Frida. So I think at this point we've illustrated to you that Frida is a very powerful tool. It can be used in a whole load of different ways. Regardless of how far you're willing to go as a developer to protect your code, if you're using basic checks, medium-level checks, and very advanced checks directly interfacing with the kernel, if an attacker is skilled enough, they can follow you there. So one of the detections we can do is actually detect Frida itself. And we've shown you a bunch of different techniques with jailbreak detection, and those can be applied for Frida detection as well. In this talk, we're only looking at these two examples, but this is just to illustrate to you that these techniques we've shown you can be applied for any detection. If you're wanting to do debugger detection, emulator detection, you'd be using much of the same techniques. So how would you go about actually detecting Frida? Well, you could look to see if it's loaded in libraries for Android, so looking in proc/maps. You can check to see if Frida is found on disk, so similar to the example that Grant was showing with jailbreak detection, looking for Cydia. You can check for Frida server itself on the disk and look for any configuration files that it's using. Or we can do even more advanced checks where we actually look for Frida in memory, so we're looking for Frida signatures. So the trampolines that we showed you, you can actually detect that programmatically as well. And you can also look for strings and functions that relate to Frida. And another basic example is just looking for Frida network activity. So we haven't really described to you how Frida works underneath the hood, but essentially what it does is when it communicates that information back from the process to the host, it does that over a port. So you can essentially listen on that port and see if it's sending information.
Why wouldn't you just detect the feature?
Because like we said before, if it can be used in multiple different ways, so you can use Frida gadget to compile it into the application on a non-rooted device as well. But also detecting on the port isn't, an effective solution because you can move the port that Frida works on as well, so it's really a cat and mouse game. So what a basic detection looks like, really basic in this example, is we're simply looking to see if Frida is operating on its default port, which is 27042. If it is, we know it's on it. If not, we're all good. And what this code actually looks like, you don't have to worry about the stuff up top. It's just initializing the struct for bind. But we're using the bind API, which essentially tries to listen on a port. So if we try to listen to Frida's default port, so 27042, if we're able to, then we know nothing's using it. But if we're not able to, we have a pretty high assurance that Frida's operating on that port. And obviously this is pretty, prone to false positives. You can do some additional checks here and see, okay, those strings look like it matches Frida. It's sending some sort of information that matches a signature. Can anybody guess what tool we would use to bypass a Frida detection? It's Frida. So in this example here, again, we're just looking for the bind API. We're checking to see if they're using the default Frida port, so 27042. If they're on that port, we just push it to something else, to 27043. And what this looks like in our test application, Frida's, despite us hooking the application, the Frida check's bypassed. So that's a really basic example. How can we take this a step further? Similar to how Grant showed you some syscalls, how can we take it further for Frida? Well, without going into too much detail about assembly instructions, because I'm sure all of you don't want to read ARM64 code, in this example here, you can see we've got the open functions, or the open instructions. If we were to hook the open function, you can see that we've now inserted a bunch of different instructions in. So a load register, a branch, and a long value. If we were to hook a different function, say access, you can see that the Frida's trampoline is consistent between the two. You can check for the signature because it's obviously inserting the trampoline each time it's inserting it. And what this actually looks like practically, we've put together a demo application that just has this check in place. For the purposes of this, we're simply checking to see if the open function's hooked. So we're calling out to it, we're checking to see if the trampoline's there. If it is, we're printing the result. So you can see when we press the button there, the function's not hooked. But when we run our hook here and hook the open function, Frida at this point would have injected the trampoline into the open function, which we can now detect when we press the button. And as Grant mentioned before, there's a whole host of different tools that allow you to do this. Frida is just one of them, but there's similar signatures you could find for other tools. For example, Substrate on iOS or Exposed in Java. So with that, let's talk about some considerations when it comes to securely designing app hardening. I think one thing that's important to note is that inconsistency is favorable. You want to distribute your controls and randomize your controls. So you want to make sure that they're all, not on one very sensitive login function. You want to have them spread throughout the application in sensitive and non-sensitive places. And you want to consider adding entropy to your controls. Instead of having, one jailbreak detection on your login page, have 10 jailbreak detections, run 10% of the time. So that makes it even harder for an attacker to pinpoint one of those detections each time the application runs. And it just makes it pretty painful for somebody to reverse engineer how they're being crashed from the app. And you want to make sure that you react in multiple different ways. You can get really creative with it. In the example Grant showed you, just using exit, you can easily disregard what that's doing. We've seen applications out in the wild when we're doing bug bounties and that kind of stuff that will intentionally mess up the stack, and then later on the application's lifecycle, when it tries to access something, it will then die of its own accord because it's intentionally messed it up. So you can do stuff like that to make reverse engineering very, very painful. And you want to layer your controls with controls and layer those controls with controls. So make it so they have to defeat 3 controls once they break. So they break one jailbreak detection, but you've got a jailbreak detection that checks to see if the first jailbreak detection is a lock. So you want to layer it as much as possible. And again, like I mentioned before, today was just an introduction. You want to consider adding, lots of different app hardening techniques depending on your threat model. Debugger detection, emulator detection, there's a whole host of different things out there to consider. But today we've really just given you the basic techniques. But there's a whole host of things to consider. So some closing remarks. I think if anything, we've illustrated that app hardening is a cat and mouse game, regardless of how far you're willing to go as a developer, whether you're using, Objective-C calls, or syscalls. If an attacker is skilled enough, they can follow you to that level as well. And because of that, the controls you're putting in your application at this level are not comprehensive. It's by no means, a substitute for a well-architected application. It's just one layer as part of that defense in depth approach. And your main objective with app hardening is really just to raise the bar of difficulty. You want to make it as hard as possible for somebody to get any reward. And with that, it's not impossible, to make somebody break it. It's just about making it not worth the time investment. You want somebody to go into the App Store, see your application, decompile it, look at it and say, that looks horrifying, move on to something else. And you want to, just to make their lives as time consuming as possible to get any reward. And I feel like it's worth mentioning as well that app hardening is not easy. As Grant said, if you're using copy-pasted controls from Stack Overflow, it's probably going to be easily bypassed. There's probably things out there already that bypass them. You should probably consider using a commercial product if you're very serious about it, because they've been looking at this stuff for a long, long time. And with that, are there any questions? Yes, sir.
In terms of app hardening, like how often do you actually find companies do it? Like to an effective level? Do you, for like in your day-to-day, if you're reverse engineering mobile app, how often or all would you see that they're actually doing effectively?
So I think it kind of varies. We've seen a lot of commercial products that do it very, very well. I'm not sure what your experience is with actually seeing companies do it themselves.
Yeah, for the most part, as I say, we picked 10 random apps in gaming, medical, and banking, right? And there is a trend to that graph. It's only a sample pool of 10. The mileage doesn't go very far. It's nothing scientific, but it is generally what we've seen. I would say it's started to become very common in finance. The gaming world has been doing this outside of mobile for a long time, so to try and prevent like cracking of games and cheating engines and stuff like that. Some Riot Games, the guys behind League of Legends, they have like a fantastic blog post about like detecting scripting engines and stuff like that. But yeah, it's not even the case that not every app does it, but not every app needs to do it either, right? It is purely, as Nick said, it depends on the threat model. It's not a replacement for like a secure, well-written app, but in some cases, there are apps out there that are likely to get targeted by more interesting adversaries than, let's say, a marketing app, for example. So I think in the gaming world and in finance, it's more often than not. And if we're doing pen tests, like generally we're not looking at this stuff. We have specific engagements where we would look at this stuff. So what you'll find in the industry is if you're working on apps that do this, generally they give you 2 copies. So they give you one with everything turned off, and they give you one with all of the stuff turned on, so that you can actually vet that it's working as intended. And then you get other engagements where you're actually targeting, like whether or not you can bypass it, whether it's actually effective, whether the obfuscation is sufficient. So that stuff tends to be a lot more interesting. But day to day, for the most part, most people just want you to vet that it's there. Like usually they do some kind of analysis themselves. I've worked for some people comparing commercial products and things like that. So certainly becoming more popular.
I think something important to note is that like it tends to be like the extreme of each spectrum. Either it's really bad or really good, and then the in-between seems to be missing.
The best apps tend to do something with commercial products, but they also do
combine it with something else. Yeah. Anything else? Yes, sir.
This type of hardening is actually harder, like for you, or doesn't seem that has
So something that I think is important to note is that this can have impact, right? If you're using some sort of commercial product to obfuscate your code or add some of these detections in for you, that has side effects as well. So for example, if you build an application with these controls and then ship it to production and then something happens, that can often be an absolute nightmare to reverse engineer what happened. So if something crashed and you're just sitting there like, could have been anything under the sun really. So it does have an impact for sure.
Yeah, I think specifically, like you're saying, if you have, these teams are collecting like analytics from all the crashes and failures in the apps, like you're saying, and if you've renamed all the methods and class names to absolute gibberish, and then you say to the developer, yeah, the app's broken, here's the 100 crashes, and it's just gibberish, but as all he can see is the source code, So the dev team, he or she, they're just working with the names that they expect to see, but when it hits production, they're all gibberish, so the crash logs have to be converted back, and in the beginning, they didn't have automated tooling to reverse that process, so it was just like, yeah, this is not usable. But also, as you say, it's adding complexity. It's adding performance hit. You have to explain to the team why the app size is now 20% bigger, the download's bigger, and people have, like, data limits. Not so much of a problem now, but back in the day, like, people had, like, limited data limits, and, convincing people to make the apps bigger and stuff is not always easy. But yeah, it definitely does.
Same app on iOS, not really for any difference in history or is it generally
from an app hardening perspective, or just so I think in terms of commercial products, they usually tend to be in line, but it really varies from company to company. Usually, they have separate development teams for each platform. So sometimes, for example, you can have a very secure Android application and the iOS application can be miles behind. So it kind of varies dramatically. I'm not sure.
Yeah, I think I don't know how many people went to the malware stuff, but it's very common in the malware space to have things like code packers, and again, code packers have been used in things like protecting your apps and games from cracking. Code packing is a technique that typically is used on Android apps that are trying to heavily obfuscate them, but code packing is not a thing that you can utilize on iOS, so that is one of the main things that you don't really see. So, working with a colleague, and he's got like this crazy Android app that's just bonkers, and like even to get into the code and actually to see the code is hard. And I'm just like, yeah, the function's right here, like return false. Okay, yeah, I'm good. But on the Android side of things, he's just in a mess for like 3 or 4 days. So there's definitely some differences, but when you get to some of these controls, like Nick said, the parity is pretty common.
I think something that's important to know is like the static analysis portion on Android. Like in the example I showed you, when you kind of go above and beyond, you can end up with absolutely wild things on Android. Whereas on iOS, it often isn't that painful.
It's less common. I mean, one of the fundamental problems with renaming stuff on iOS, for example, is like if you rename anything that touches a user interface, it just breaks, just shits itself. So yeah, again, you tell the team, you run this tool, renames everything, and they go, oh, fantastic. The app won't even start. So they're like, yeah, no, like just get rid of it. Right? So it's you do end up having differences, but most of the time it's almost one for one.
Sorry, can I just finish this here?
Yeah.
We're running quite close to time, so.
Yeah, thank you very much.